Welcome back. We're going to start subsection 6.6.2 on the algebraic properties of the determinant. Theorem 6.6.3. Let A and B be n by n matrices, let C be an invertible matrix, and let K be a real number. Statement 1. Determinant of A transpose is equal to the determinant of A. So we're not going to prove these, but we are going to give reasons, motivations as to why this is a reasonable thing to believe. And the first thing here is that the rows of A are equal to the columns of A transpose. That's what transposing does. And then the cofactor expansion along the row I of A, well, that's going to be the same as the cofactor expansion along column I. If rows are columns and columns are equal to rows because of the transpose, then the cofactor expansion along row I of A is going to be the same as the cofactor expansion along column I of A transpose. And since we're allowed to choose any row or column for the determinant, then those two values are going to be equal. Statement 2. Determinant of K times A is K to the n times determinant of A. Now this little exponent n is, my guess anyway, the most forgotten exponent in the history of mathematics. So why is this true? Well, the first thing is that scalar multiplication, so scalar multiplication, is like n row operations. So let's take a look. If we start with A and we multiply the first row by K and we get some matrix, and then we multiply the second row by K and we get some matrix, and we keep on doing this, then when we multiply the last row, we've ended up by multiplying every single row by K, which is exactly what scalar multiplication does. And each of these row operations, so each row operation multiplies the determinant by K. We'd seen that in a previous video. And so if we're doing n operations, means that we're multiplying by k n times, which is the same thing as k to the n. Determinant of AB, statement 3. So this is determinant of A times determinant of B. So that is actually a little bit more involved to prove. It's not so easy to see why just that should be true, but we're going to accept that. We're going to take that on faith that the property in fact does hold, and we're going to use it here in number 4 as part of our reason. So determinant of C inverse, 1 over the determinant of C. And now you might be wondering, can something go wrong? Could that be 0? Can we be dividing by 0? And the answer to that is no. C is an invertible matrix, and we'd seen in a previous video that the determinant has to be non-zero for C to be invertible. And so this is a well-defined statement at the very least. And the reason that that is true is the following. Well, if we multiply C inverse by C, we know that we get the identity matrix. So if we take the determinant on both sides of that equation, then the determinant of C inverse times C is the determinant of I. And if we believe statement 3, then we can apply it here and separate that product. So we get the determinant of C inverse times the determinant of C, and that's going to be equal to the determinant of I. But we remember that I is a diagonal matrix, 1's on the diagonal and 0's everywhere else. And so the determinant is the product of that diagonal, which is 1 times 1 times 1 times 1, which is just 1. And so then if we want the determinant of C inverse, then all we have to do is solve for it now. And so that is telling us the determinant of C inverse is indeed 1 over the determinant of C. So please join me for the next video where we will go and apply these properties to solve some problems.